Hello, students. We're going to talk about two big concepts as they apply to rotational inertia, and really how we can write expressions for the rotational inertia of systems when they're, well, in a couple of different ways, okay? There are certainly tables that tell us what the rotational inertia of some forms are around some common axes, and what we will talk about is how to derive those in a couple of ways, and then how to derive rotational inertias in other cases when the axes around which objects rotate aren't, quote, standard axes. So the kind of the primary one is called the parallel axis theorem. And so in our figure, this guy here, this figure above, what we're saying is there's a rod and it's rotating about an axis. It's rotating about this axis, okay? And what I've identified on there is, well, the rod has a center of mass. This is a uniform rod of uniform linear mass density, let's call it. So its center of mass is where it is. And there's an axis that passes through that center of mass that's parallel to the axis around which our object is said to be rotating, right? So this center of mass axis is parallel to our rotation axis because we choose to draw it that way. And so when we do that, we can employ the parallel axis theorem that says, well, this object is this rotating rod is kind of two things. One, it's a point mass. It's an object. That's an A. That rotates around the axis. All right, so the object, simplified as a point at the object's center of mass, moves in a circle around the rotation axis at a distance that most texts call h, or the theorem, I guess, in its standard form calls h. And so there's a point mass rotational inertia of this thing, mh squared, assuming this rod has mass m. Fair enough. So we're saying, you know, a point mass's general rotational inertia is mr squared, little r squared, where r is the distance from the object to the axis around which it rotates. And then second, we can look at this thing as an object, the rod itself as an object that rotates around its own center of mass. Because if you consider, you know, this end of the rod, well, when this whole thing has swung around like this, and this end of the rod that's, quote, pointing to the, you know, down and to the right will now be pointing up and to the left when the thing has rotated through a half a rotation. So the rod itself rotates, and we can say it rotates about its own center of mass. So the object, now considered an extended body, rotates around its own center of mass. And we happen to know, so there's what we call what I call ICM, and that has whatever form it has. In this case, and I mean algebraic form, in this case, the rotational inertia of a rod about its center happens to be 1/12 ml squared. All right, so we could say that this rod now about this axis that's parallel to an axis that passes through its center of mass is, well, the sum of these two things. So this is going to be 1/12. It's going to be, for this one, 1/12 ml squared plus mh squared. Fair enough? That's for a rod around some, around some arbitrary axis. Let's use that to talk about a rod about its end. Now, we happen to know that a rod about its end, you know, from a reference table sort of thing, is going to be 1/3 ml squared. So let's see, assuming that we know that a rod about its own center is 1/12 ml squared. Well, here's a rod rotating about an axis like this. Here's the center of mass axis, and here's our distance h. And if this thing has a length L, then our distance h is L over 2. So this thing, if we say, the way I write it is I parallel, I write it as I point mass plus I center mass. All right, so this I is, let's see, the point mass is saying this thing rotates in a circle around our chosen axis at the end of the rod in this case. So that's mh squared. You get me? H is L over 2. Okay, and then plus, well, we happen to, again, assuming that we already know that the rod about its own center is 1/12 ml squared. Okay, so that's 3/12 ml squared plus 1/12, that's 4/12 ml squared. And yeah, I parallel is 1/3 ml squared. All right, we have just, in one way, defined that a rod rotating about its end has that rotational inertia. Now, we already sort of, quote, knew that, but we only know it because someone told us, right? We see it in a table of, hey, here's some rotational inertias to know, right? Right. Okay, what about a, a disk? Okay, about a location. So, I don't know, what's this crazy thing? This is a disk rotating about a axis that passes through that place. Now, let's assume that we know that a solid disk's rotational inertia is 1/2 mr squared. We have to assume that for now. Okay, so this thing, well, our I parallel, I write it as it's an object moving in a circle. It's it's also a form, an extended body that rotates about its own center of mass. All right, so what we're saying is this thing sort of swings around like that. Okay, so let's see. I point mass here. Well, here's our H. That happens to be, so that's mh squared, right? So H is R over 2, so R squared over 4 plus, well, 1/2 mr squared. So it looks like we get 1/4 mr squared plus 1/2 mr squared, and this thing happens to have a rotational inertia of 3/4 mr squared. Okay? Now a solid rolling sphere, and rolling, I'm sort of looking ahead a little bit to when we talk quite a bit about objects that roll, or particularly roll without slipping. I'm going to have you try to do that one. Let's assume that we know that a solid sphere rotating about its own center of mass has a rotational inertia 2/5 mr squared. It should be fairly easy to show that the rotational inertia of this rolling sphere, like across the floor, is 7/5 mr squared. The solution has a hint in it. Okay, so make sure you can see if you can get there. Now, how is it that we get these? You know, where the heck is that? Where's this from? Whoops. Where's that from? Where's this from? Where's this from? How do we get these expressions? Well, they come from the idea of, you know, how can we go from the rotational inertia of, say, a bunch of discrete objects to the rotational inertia of an extended body. All right, and let's say that we wanted to pick an axis of rotation. Well, I don't know, let's just pick an arbitrary one. Let's just say, you know, there's an axis around which we're trying to identify this object's rotational inertia. Well, by definition, what we have to do is we have to talk about, I mean, you know, what I'm trying to show on the top is, let's say these are actually a bunch of discrete objects. All right, well, what we would do is, this is the sum of all the rotational inertias of each of the objects, right? And that in this case, because these things are point masses, well, that's going to be R, so well, really, mr squared. And maybe we do, well, it's the sum of all the combinations of that. Okay? Well, when we move to an extended body, what we say is this thing is not made of discrete objects, but it's made of an infinite number of little tiny objects. There's one of which, I mean, you know, I'm trying to say there's a slice of it that I've made a little slice here, and there it is. And well, this object is located at, you know, that distance r from our axis of rotation. It has a mass, but that mass is really, really small. So it has a infinitely small mass. So this turns into not the sum of all discrete measurable rotational inertias of objects, but, well, the sum of all the infinitely small rotational inertiae of the things that make this up. All right, now in this case, this thing happens to be made of point masses. All right, and so in this case, the point masses rotational inertia is, well, we usually, instead of writing it as dm r squared, we'll write it as r squared times dm. Same thing, we're taking that product. All right, and the reason we write it this way is because we're going to integrate with respect to m. Okay, so, well, that's it. You know, I'm not going to do it. I'm going to do a couple in the subsequent slides, but you know, what we need to be able to be, what we need to be able to identify or be okay with is that a summation um, of discrete products turns into an integral of a quantity. Or is that the right way to say it? I don't know. This integral, where integration in this case really means add up all the infinitely small things. All right, here's the look, quite literally, add up all the infinitely small things. Now the big deal here is di is the rotational inertia of your dm. Notice, in this case, our dm is a point mass, and a point mass rotational inertia is mr squared. Now, quite literally, what we do is, if we say there's this expression, I point mass is mr squared, we can differentiate that expression with respect to m because we want to get a dm. So watch, di dm is, well, r squared, and so therefore di is r squared dm. There are cases in which you will not make an extended body out of point masses. And when you don't, you have to go through the step of saying, well, what is, well, really, yeah, what am I making my form out of, and what is the rotational inertia of that elemental part? Okay, so let's do a couple of derivations. All right, let's say a rod about its end. Now we know what the answer is. Quote, we know, right, because we've seen it before. But if we say, okay, here's a dm. Now we're going to say this thing has a length L, it has a mass m, and it has a, that's an underline, it has a density lambda that's defined to be m over L. So we can say, let's see, the rotational inertia of this object is the sum of all its elemental rotational inertias, right? We showed in the last page that that is r squared dm. All right, so what's my dm? Well, my dm, how massive is this little part? That depends. It depends on how dense the form is, and, well, this spatial dl, that comes right from here, right? If lambda is m over L, then m is lambda L, and if we differentiate dm dl, we get lambda, and therefore dm is lambda dl. Big L or little l here, no big deal. Okay, so this is now r. Well, r is that. There's r. And dl is a dr, right? It's a distance along in the direction of our r, of our r. So that means we can write this as, let's see, r squared lambda dr. Yeah, where our r's vary from nothing all the way out to L. Where can these things be located? Well, the first one's right here. The last one's all the way at the end. So that lambda is a constant. We can pull that out. I'm going to write that as m over L. And then we integrate r squared dr from 0 to L. So that gives us m over L r cubed over 3 from 0 to L. That gives us m over L L cubed over 3. Well, formally, technically, minus 0 cubed over 3 if you want to. Okay, and that is ml cubed over 3l, or ml squared over 3, or 1/3 ml squared. Hooray. Guess what the only difference here is? If we say that we are going to evaluate about the center, well, is everything's the same except, okay, we can say, yes, r squared lambda dr. Our r's now go from over here to over here. Okay? So that's m over L, r cubed over 3 from negative L over 2 to positive L over 2. That should be, yep, okay, fine. So that means that's m over L. Let's see, L squared, no, sorry, L over 2 cubed is L cubed over 8. I'm going to pull this 3 out too. You get me? And then all we have to do is this. L over 8 minus, well, negative L over 2 cubed is negative L over 8. These are both supposed to be cubed. And that's 2 L cubed over 8, or L cubed over 4. So this is I is m over 3L, L cubed over 4. And lo and behold, that is 1/12 ml squared. I say check because we, quote, know that's true. Okay. All right, now, a disk about its center. We know, quote, the answer is I disk is 1/2 mr squared, where this thing has a spatial radius r. Let's say it has a mass m, and it has a area density m over a. And guess what we're going to make our disk out of? You're going to make it out of really thin hoops that have a radius little r and a width this way of, let's call it a dr. And they have a little mass that depends on how dense this stuff is that the disk is made out of and the area of that little hoop. Well, the area of that little hoop is, well, its length times its thickness, so that's 2 pi r dr. And if we say that I, this is an important first step, right? We're saying that we're making this thing, my di is a hoop. All right, well, a hoop has a rotational inertia, quote, mr squared. All right, so our di of a hoop we can call r, well, it's not going to be big R though. Each one of our di's has a radius little r, and then we use times the little mass. So then, when we say I is the integral di, well, okay, so we are still r squared dm. We just went through some pains to show that this is r squared sigma 2 pi r dr, where r varies from nothing to big R. So let's see, that's a 2 pi sigma r cubed dr from 0 to r. I'm out of time, folks, so you can run this integral, and you can see, you will show that this gives you what you want, 1/2 mr squared. Okay? I can do it. I'm right here. Come on. Come on. So, all right, watch. This is 2 pi. Sigma is mass over area, pi big R squared. And then we're integrating, well, we've already integrated. Let's call it R fourth over 4 from 0 to R. So that's, let's see, we get a 2m over r squared, r to the 4th over 4, right? Here's the r to the 4th over 4 when we evaluate our integral from 0 to r. And yeah, that gets us there, right? We got those go, there's a 2 that goes, there's a 2, and yeah, we get that our disk is indeed 1/2 mr squared. Hooray. Okay? Things get a little trickier specifically in this one. This gets trickier for one main reason. But I'm not going to tackle that here. But I'll tackle it specifically on its own. Okay? Really well.